Any questions about last session? So last session, we finished up semantic segmentation, and we finished with this paper. That was combining the encoder-decoder structure of a unit and the actual separable convolutions. And the idea was you wanted to do semantic segmentation, basically pixel-wise classification. Now we're gonna change the tone a little bit and consider somewhat more classical problems in computer vision. For instance, super resolution. It's a classical problem. Denoising, colorization, depth estimation. And these methods have applications in games, in video games, video gaming. That's one application. For instance, you might have a low resolution image, and it's a low resolution rendering of your 3D environment. Now what you can do is have a neural network in between that's taking a low resolution image and making it super resolution, basically increase the resolution. And then it's going to increase the quality of your video games. And that's actually what NVIDIA is doing for their deep learning super sampling and super resolution. That's exactly what they do. For denoising, again, you're going to have applications in exactly like Sricharan is saying, what is DLSS? That's exactly what that is. The other one is denoising. When you do your ray tracing of your 3D environment, you're going to end up with a noisy image of the environment. But you cannot show your gamers a noisy image because they cannot play the game. They're not going to be happy about your product. So you have to denoise it. And basically, you have a noisy image. You want to transform it into a noiseless image. Same thing for colorization, and depth estimation is going to have applications for self-driving cars. You want to know how far that object is from your car, etc. So there was a question, what does DLSS stand for? It stands for Deep Learning Super Sampling. And thank you, Kevin. And the other application could be for these days that we are all, for instance, and we are having our meetings over Zoom, and the idea is that you want to transfer through the internet a low resolution image and then have some post-processing on the computer of the person who installed Zoom, for instance, to do the super resolution. Then it's going to increase the quality of the images while making it cheaper to transfer one image to the other end, from one user to the other user. So these are the applications. And let's start with the first paper that tried to consider solving this problem using deep learning. Prior to deep learning, people were doing a three-step process. They would extract some patches from their image. They would then create a representation of those patches. Then they would take those representations and the patches and push it through a nonlinear mapping. And then in the end, they would do a reconstruction step. So this paper came along and said you can replace all three of those steps with convolutions. We know that convolutions are gonna extract patches on their own. This is gonna be a sliding window of your input image. So the patch extraction is straightforward with convolutions. The representations, we are gonna learn it with a bunch of weights or a bunch of filters. For instance, your filter could be of size f1 by f1 by n1, and that's going to give you your feature maps, and that's going to give you the representations that you were looking for. Then nonlinear mapping is a one-by-one convolution. That's going to give you a bunch of transformed feature maps. Let's say you have n2 of them, and then the rest of it is reconstruction. What is the value of this pixel? You're going to take those features and then convolve it with a filter, and then that's going to give you your high resolution image. Now what you're going to do is feed this with data, and you need to come up with an appropriate loss function. So let's try to make things more rigorous, more mathematical. So your first low resolution image, first you need to do an interpolation on it for it to have the same number of pixels as your output. So that's the first step. You take your low resolution image, you pipe it, you push it through a bicubic interpolation, and that's going to give you y, your interpolated image, and this is y. What you want to do is this network is going to give you a nonlinear function that's going to give you f of y, and f of y is going to be your super resolved image. And therefore, you want it to be as close as possible to your high resolution image, to the one that you started with. I know you're used to X going through a nonlinearity and then giving you Y, but notation wise, Y is going through a bunch of nonlinearity and it's giving you something similar to X. So let's see what is the patch extraction step. That's just you're convolving your input with your filter and then applying the ReLU activation. So that's for F1. F2 is gonna get the output of F1, convolve it with a bunch of weights. Now this time these are just one by one convolutions. And then you do ReLU, that's the nonlinear mapping. For the reconstruction, there is no nonlinearity. You just convolve it with the output of F2 and then add your biases, and that's gonna give you F3. And the entire thing is gonna be your nonlinear function. What is your loss function? You have a bunch of parameters, theta. These thetas are W3, W2, W1, B1, B2, and B3. Your function is parameterized by theta. It's taking as input a low resolution image, and then you want it to be as close as possible to your high resolution image. And by the way, generating data for the super resolution task is very simple. You start with a high resolution image, and then you make it low resolution. That's it. You start with X, and then you make it low resolution. So it's easy to lose information, and then you're going to lose information. So generating input-output data for this task is very easy. As long as you have high-resolution images, you can train this with as many data as you want. So there is no transfer learning going on here because you have enough data. So a bunch of jargons. SRCNN stands for the method in this paper, Super Resolution Convolutional Network. Sparse coding is an alternative method prior to deep learning. And the way that you measure how good your predictions are, how good your algorithm is performing, is using peak signal to noise ratio. And this has a formula very close to your loss function. And there is debate whether this is the correct way of measuring how good an algorithm is doing or no, but we don't want to worry about the debates in this class. We're just going to use that. But there is a high correlation between this loss function and the evaluation metric. So how is the algorithm doing? It's giving you 32.6, 32.5, 32.26 for peak signal to noise ratio. And what is changing from one panel of this table to the other one is the number of feature maps. And 128, 64, or different sizes. So the smaller your network, the faster it's going to be. So this is really fast to do your super resolution. And how do you compare to the previous state of the art prior to deep learning? This is bicubic interpolation. This is sparse coding. And this is the deep learning method. And what you are reporting is peak signal to noise ratio. And qualitatively, this is how the predictions are going to look like. That's the original image. And we are going to zoom in onto this part of the image because we want to focus on how good the algorithm is doing in super resolving. So we have to zoom in on parts of the image. This is bicubic, this is sparse coding, and this is what the deep learning method is doing, SRCNN.
Can I ask about the generation of the low resolution from an original high resolution? Do you do that just by, I guess, averaging like maybe a 2x2 pixel into one sparse pixel, or do you do subsampling and just throw out every other pixel left and right and top to bottom?
Just throw it out.
Okay.
It's very simple. You pick some of the pixels and you pick it, you keep it, and then you drop the rest.
And then you just make those pixels bigger and then you have the same image. Okay.
Yes. So that's pretty straightforward. It's not that complicated.
And then
it's easy to lose information.
The bicubic here in this table of the errors, it has constant error, and it's because the bicubic interpolation formula is deterministic, so it doesn't depend on anything else, right?
No, there is no optimization going on.
Got it.
These are the iterations of the optimization.
Yeah. Okay.
So there are a bunch of other methods that we are comparing with, and you can have SRCNN. You can actually train SRCNN on images in ImageNet, and you have a lot of images in ImageNet. And you don't care about the labels. You don't care whether it's a dog, whether it's a cat, whether it's a building. You don't care. You just take the input image, and then you make it low resolution, that's going to give you the input output data.
I'm familiar with signal to noise. What is considered the noise in this case?
You can think of your low resolution images as noisy versions of your high resolution image, because at one location where you had information in the high resolution image, the value is not the same. If you just copy and paste it here, it's just going to be a different value. So you can think of low resolution as noisy images as well. It just doesn't have the correct value. If you look at a point here, it's not going to have the correct value if you copy and paste from your low resolution image.
So the noise itself would be the difference between the high resolution and the low resolution if you just copied it with the 4 neighbor cells back up to the dimension of the high resolution and took a pointwise difference.
Yes, so that's going to be your noise.
Okay.
Okay, and then you can qualitatively compare the predictions of this model and previous state of the art. So this is the first paper, to the best of my knowledge, that's using a convolutional neural network for this task with some success.